We can now start working with the force of a spring. The force of a spring is equal to negative kx. The force due to a spring is equal to negative kx. Remind me, what is k, Loki?
The spring constant.
K is called the spring constant. What are the most typical dimensions on the spring constant? Garrett?
No.
That would be a coefficient. It's not the spring coefficient, it's the spring constant. Okay, who can tell me what it is and tell me how that equation helps me to know what the common dimensions are? John?
Force over meters.
And what are the dimensions for the force?
Newtons.
Newtons per meter. You kind of answered both questions at the same time there, right? Because we solve for the spring constant, we get force over the x, the position. And so it ends up being newtons per meter. What is x? X, Tim?
Displacement from equilibrium.
It's called the displacement from the equilibrium position. The equilibrium position is also has another name. We use it almost interchangeably. What's the other name for the equilibrium position? The rest position. Rest position. You'll see me here, or you'll hear me call it both. So it's a displacement from the equilibrium position or the rest position. What does that negative mean? Tip.
Direction.
All it indicates is the direction. This means that the negative means that the force on the spring is opposite the direction of the displacement. That's all that negative means. And we'll make sure you know how to use that by doing this example. Let's say that we have a mass which is equal to 1.0 kilograms, and we place it on a spring with an unknown spring constant. So initially, the spring is hanging like this, and when we add the mass, the spring is now hanging like this, and it goes down a distance of 4.0 centimeters. The first question is, it goes down 4.0 centimeters and stops. The first question is, what is the spring constant of this spring? First step in solving for the spring constant of this spring, Travis. We know the equation. We're not going to do that. We'll get there eventually.
Isolate K.
We don't even have an equation. We can't do that yet. Help us out, Emily. We can't. I can't sum the forces yet. Bailey. We have to start with a free body diagram. Before we can even sum the forces, before we can start with an equation, we need a free body diagram of the forces acting on this mass. Michael, give me the forces acting on the mass. FS stands for? F stands for? The force of the spring, what direction?
Up.
Up. How do we know that the force of the spring is up, Andrew?
Because it's opposite the displacement.
The displacement was down, therefore the force of the spring is going to be the opposite direction. Michael?
I guess
FG.
No, force of gravity.
The force of gravity is down. I agree with this. We have our free body diagram. We can now sum the forces. We should sum the forces, I would suggest, in the y direction. If we sum the forces in the y direction, we will get the force of the spring minus the force of gravity equals mass times the acceleration in the y direction. What is the acceleration in the y direction, Bill, of the mass? No, the acceleration of that mass. Look at it. Right. Remember, it stops. So it stops. So the acceleration in the y direction is equal to 0. The force of the spring minus the force of gravity equals 0. Therefore, the force of the spring is equal to the force of gravity. What now? Hamza?
We know that equals energy.
I agree, the force of gravity is equal to mass times acceleration of gravity. What about the left-hand side?
Force of spring equals energy.
Right, I agree with that, but we know something about the force of spring.
It's negative. Force of spring equals.
You're missing it, that's okay. Sierra?
Should we just put in KX?
KX or negative KX?
KX because we have our free body diagram.
This negative just gives the direction. By drawing the free body diagram and summing the forces, we have already identified the direction. If we put in the negative again, we negate the direction. We put it 180 degrees from the direction we wanted it to be. It doesn't work. So we've already included the direction of our free body diagram, so we use the magnitude of the equation, which is k times x. In other words, the spring constant is equal to mg over x, where m is the mass, 1 kilogram, g is 9.8, and x, I'll convert to meters, is going to be 0.04 meters. The spring constant then is equal to 245 what? Bill? Newtons over meters. Is it exactly 245?
Yeah.
Because we only have 2 sig figs, so what does it round to? 240. Nice. It's that arcane rule, is it? 240 newtons per meter. Great, so that's the first part. We have figured out the spring constant of this spring. We've used the equation to force the spring. We understand how to use that negative in the equation. Now we're going to figure out the work done by the spring. Work done by the spring. We have 2 different choices of equations we could use for the work done by the spring. Give me one of them. Tyler.
You could use F delta cosine theta.
Sure, that's fine. You could say it that way. That's fine. Or we can use the work due to the spring is equal to what, Emily?
The force times the dot product.
Oh, that's the same thing as that one. I'm talking about a different equation. That's okay.
Integral.
The integral one, which is?
The integral of x from x initial to x final of the force of the spring constant
Okay. Which one do we use and why? Left.
The integral one is not constant.
You cannot use this one because it is not constant. Because the force changes with position, we cannot use f d cosine theta. All right. So let's figure out the work done by the spring. That's going to be equal to the integral from the initial to the final position. The initial position is 0. The final position is negative 0.04 meters. The force of the spring, the equation is negative kx with respect to x. Please take the integral of negative kx with respect to x. Victoria. Negative kx squared over 2. Relax. We go from 0 to negative 0.04 meters. Let's take a mild detour to talk about this. 1/2 kx squared. That looks familiar. It is, Emily?
Potential energy.
This is the elastic potential energy stored in the spring, which is the negative of the work done by the spring because it's the energy stored in the spring, which actually makes sense when you look at it. So that is where the equation for the elastic potential energy comes from. It's the negative of the integral of the work done by the spring. Okay. We know the spring constant, it is, actually we'll just plug in all sorts of stuff here. We got negative kx final squared divided by 2 minus our negative kx initial squared divided by 2 from 0 to negative 0.04 meters. So it's equal to negative 245 times negative 0.04 squared divided by 2 minus 0.
Negative.
Negative 0.196 what, Nick?
Wait. Joules.
Why negative? Why is the work done by the force of the spring negative?
Oh, because it's the forces are opposite each other, or 180 degrees apart.
Ah, the
The
force
direction and the force.
Ah, the direction of what?
The displacement.
So remember, it has to do with the force you're talking about and the displacement of the object. The force of the spring is up, the displacement is down. Therefore, therefore, it makes sense that the work done by the force of the spring would be negative. Good.